Hello and welcome back. Last video we solved a question on internal resistance. We actually derived an equation to solve questions that are related to internal resistance. In this video we will solve two more questions on the same topic. This first question is just, you can say, a revision or review of the equation that we derived last time. And the second question that we will solve today will be a more deeper understanding of the equation. We'll focus on the graphical understanding of that equation, right? So if you plot that equation on a graph for different variables, how will the graph look like, or how should the graph look like? So let's start with this question. The question is, a cell of EMF E and internal resistance R is connected across a fixed resistor of resistance R. There is a current I in the circuit and a potential difference V across the fixed resistor. The term lost volts refers to the difference between EMF and the terminal potential difference. So I explained last time also that the EMF is the voltage developed by the cell between these two plates. This is the positive plate and this is negative plate. This is the EMF generated by the cell. But this EMF is not the same as the potential difference that we get, or the voltage that we get at these terminals of the battery, right? So this is the terminal voltage and this is EMF, and they are not the same. The reason is this internal resistance. So let's say EMF of the battery is 12 volts, and out of these 12 volts, a small voltage is dropped across this internal resistance, which will be I times small r. Let's say this I times small r, let's say it's 2 volts, right? So out of these 12 volts, 2 volts are dropped across this internal resistance. That means that the voltage that you will get at the terminal will be less than 12 volts, which is the EMF of the cell, right? So EMF is 12, but the terminal voltage, let's call it VT, it will be E minus the voltage dropped across the internal resistance, which was IR. And just for the sake of this example, I said that, let's assume that IR is just 2. So 12 minus 2, in this case, terminal voltage will be 10 volts. You can see it's less than the EMF, right? So this lost volts refers to the difference between EMF and the terminal potential difference. If you look at this equation, so that means this is the lost volts that they are referring to, right? So if you rearrange this equation, IR will be equal to EMF minus VT, right? This is the terminal voltage, and this is the difference of the EMF and the terminal voltage. And you can see the difference of the terminal voltage and the EMF is just the voltage dropped across the internal resistance, which we called I times small r in the last video. So that means that in this question, they are referring to the voltage drop across internal resistance as lost volts, right? So it doesn't matter what you call it. If you understand this equation, you know that the difference between EMF and the terminal voltage will be the potential that was dropped across the internal resistance. So for this question, the correct option is option B, that is I times small r. Okay, now the first question was just, like I said, was just a review of what we did last time. This second question is more important, and we will learn something new in this question. That is the graphical aspect of this equation that we derived. The question is, a cell of EMF E and internal resistance R is connected across a variable resistor as shown. A student varied the current in the circuit using the variable resistor. The current I and corresponding potential difference V across the cell were recorded. A graph was plotted of V, that is potential, against current I. Which of the following statements about the graph is correct? Without looking at these options first, we will just write the equation first that we derived last time. The equation was that EMF E, which is generated by the cell, is equal to IR, that is potential drop across the internal resistance, plus I times capital R or big R, that is the voltage dropped across the external resistance, in this case, this variable resistor R. Now, this is just Kirchhoff loop rule, right? We go around the loop and we add all the voltage rises and all the voltage drops. And if you go around the loop, they all must add up to zero. And if you rearrange the equation, you get this equation that we have here. So let's try to rewrite this equation in terms of voltage V, because we are plotting the graph for voltage V against I. So I can write this as E equals IR, which is the voltage drop across internal resistance. And this I times capital R is the voltage capital V that we get at the terminal as the terminal voltage, right? All of this V is dropped across this internal resistance. V equals I times R. So I can write this equation like this. And now I have to rearrange this equation so that I can plot Y as a function of X, right? So on X-axis, I have current I, and on the Y-axis, I will have voltage V. In other words, our graph will look something like this. On the y-axis, we need potential, and we are plotting potential as a function of current I. So that means on the x-axis, we should have current. On the y-axis, we should have voltage. And from Ohm's law, we know that the graph between current and potential difference is a straight line. So we can compare this equation with the equation of a straight line, which is y equals mx plus c. We know that this m here is the slope and c is the y-intercept of the graph. So what we want to do here is we want to rearrange this equation so that it looks exactly like this equation right here. So on the y-axis, we want to have potential difference. So first of all, we will rearrange this equation so that we have V on the left side. So I'll get V, potential difference, equals E, that is EMF, minus I times small r. Now you can see by comparing this equation with the equation of a straight line, that is y equals mx plus c, that x is the quantity that we want to plot on x-axis, right? In this equation, if I ask you which quantity are we plotting on the x-axis, we want to plot I on the x-axis. So just to make it more similar, I will rearrange this equation. I'll write this term first, like this, minus I times R, and I'll write EMF here. Now, these two equations are exactly the same. That means Y in our case is V. Similarly, C, which is the y-intercept, in our case, it is E, that is EMF, and X is whatever we are plotting on x-axis. In our case, it's I, and whatever is being multiplied with I will be the slope, right? In this case, it's minus R. So that means we have a negative slope and we have EMF E as our y-intercept. So if you look at the options, you can see it's option D, that is gradient should be negative and y-intercept should be E. So this is the correct option. So just to summarize what we learned, because in the next video, we'll be moving on to other topics, I want to summarize this, this whole concept before moving on. So we start with Kirchhoff loop rule and we get this first equation, and we can rearrange this equation for any quantity that we need to find. For example, EMF, internal resistance, and the terminal voltage I times capital R. Now, most of the times I've seen a lot of questions in past papers. What they do is they will give you a graph for V versus I without giving you any of the diagram or saying anything about the equation, and they will ask you to find the internal resistance, for example. So you should remember this thing that for this equation, this is how the graph looks like, and always you will have EMF as the y-intercept and internal resistance will be the slope of the graph, right?